I'm going to talk about what frame relay is. We're going to go over all the terms associated with frame relay. You're going to have to know all those terms. Addressing concerns with frame relay, IP addressing, data link connection identifiers, and global DLCI maps, as well as how frame relay can handle broadcast messages. First thing we want to do is talk about what frame relay is and go over some of the terminology. Frame relay is a long distance, non-persistent connection, or that's what it's recommended for through Cisco. One of the nice benefits with frame relay, if I have one router connection and one line to a service provider, I can connect to multiple different destinations. They can have connections between each other, or they can all route in between me, however I want to set it up. Obviously, the more connections I have, the more money it's going to cost. But it's a very flexible, very useful connection. There are certain terms associated with frame relay, a virtual circuit. And what a virtual circuit is, it's a logical connection between endpoints. So DTE is a data terminal equipment, which is my stuff. So that's the stuff I'm going to have on my premises. The DCE is the data communications equipment, meaning the service provider's stuff. If I work for a service provider, then this may be technically called my stuff. Anyway, the virtual circuit is the connection that's established between the DTEs from one end to another. Let me get rid of that. So that's a virtual circuit. There are two types of virtual circuits: switched, established on demand, or permanent, which is kind of like a lease line, always on. An access link is my link here, my local loop link here between the DTE and the DCE. We've got an access rate, that's the speed that I'm promised when I'm sending information out to my service provider. A DLCI, data link connection identifier. What that is, it's an identifier. It's simply a number to identify a connection or a virtual circuit between my router and another destination. So if I had a router and I had connections to multiple different destinations, even though I had one actual line out to my service provider, I would have two virtual circuits. One going to, let's call this router A, and one going to router B. I have to label these virtual circuits as something, so what we do is we just use a number. It might be 10, it might be 20, it might be 200, whatever. This number that represents this circuit is a DLCI. I also compare it, a DLCI, to a phone in my office. If I have a phone in my office, I've got 5 lines on my phone, and I can number them 1, 2, 3, 4, 5. It doesn't matter what the number is. I can number them 900, 233, 3,999. As long as each line on my phone had a different number, I would still be able to associate a line with a name. Basically, the name is the number. And that's what a DLCI is. It's just a numerical representation of a virtual circuit or a conversation. NBMA, non-broadcast multi-access. Let me clean up this slide to explain this one a little bit. This is much cleaner. So, non-broadcast multi-access, NBMA. Let me start if we just had a switch and some computers. So here's a switch. The switch is a rectangular thing. The computers are these things with the smiley faces on them. And what happens with these computers is they have direct access to multiple other devices. So this is a multi-access environment. This computer right here has access to 2 other devices without having to get routed or anything like that. Direct access to 2 other devices. That's the part of the multi-access. The switched environment is called broadcast multi-access, or BMA if you want to be lazy, because this computer can send a true broadcast message. he sends a message that the switch receives, and that message in the header has a bunch of Fs. The switch floods that message out to all other devices, so that's a true broadcast message. In the routed environment, it's non-broadcast. You can't send a true broadcast out. Because what happens is, in this multi-access environment, this is the actual physical link right here. So there's one physical link going into the router. What happens is, on that physical link, there are multiple virtual circuits. There's this green virtual circuit, which takes us over to this green router over here, or I should say a blue router with a green square on it. And we've got this red virtual circuit, which takes us over to the blue router with a red square on it. I apologize if you are colorblind. Now, each virtual circuit is its own connection. So for this router to send a message to both of these destination routers, he can't send a true broadcast. If he were to send, he can't send one message that the frame relay switch would take and send out to both different destinations. What he has to do is he has to fake it. He makes a unicast message out of any broadcast that must go out of this interface and sends two messages. He'll send one out the green virtual circuit to the green square router. He'll send the other one out the red virtual circuit to the red square router. That's not a true broadcast. A true broadcast is one message that goes to everybody. So this is non-broadcast, but it is multi-access because with one line, he has access to multiple different devices. And really, he can have access to as many devices as he wants to pay for. So that's where we get the term non-broadcast multi-access. Let's look at some of those other terms. LMI, Local Management Interface. So basically, keep alives and status information between our data terminal equipment, our stuff, and the data communications equipment, the service provider's stuff. So they're important messages that tell us information about our virtual circuits as well as perform keep alive functions. LAPF, this is a long one. Link Access Procedure Frame Bearer Services. Let me just type that out. Alright, here's what we started with, link access, and this is much, much cleaner. Link Access Procedure Frame Bearer Services. What it is, it's the layer 2 encapsulation for our traffic going across our WAN links. It's a particular type of encapsulation for a frame relay line. Link Access Procedure Frame Bearer Services. Now I want to spend some more time talking about the LMI types as well as LAPF. Let's start with LAPF, Link Access Procedure Frame Bearer Services. Now LAPF is a standard for a layer 2, and again I'm talking about the OSI model. Layer 2 down here, so our IP packet. So this would be, if we're sending IP traffic, this would be our IP packet. Thus the term packet. At layer 3, it's called a packet. Layer 2, a frame. Layer 4, a segment. So our IP packet gets encapsulated with the LAPF standard. And that has a number associated with it. It's Q922. Q922 is the LAPF standard. And again, that's just our ANSI or ITU information standard, this protocol in Q922. That is for LAPF. What it does, it specifies the type of header and the type of trailer that's going to go on the IP packet. But there's something else that needs to go on this packet. Remember, layer 2 of the OSI model has two sublayers. LLC, Logical Link Control, and the MAC sublayer. This is where LAPF is hanging out, down here, the second part of the layer 2 encapsulation. If you notice something, Right butted up next to the packet is what's called a little type field there. And this is the big difference between the two types of frame relay encapsulation that are going to go across our frame relay lines. There's two standards for this. There's one standard designed by IETF, and it is called IETF, Internet Engineering Task Force. They have a multi-vendor standard for this type field. Multi-vendor meaning more than just Cisco. And then you've got the Cisco type field. That one's going to work with Cisco routers. So the LAPF, very important to understand that is the header and the trailer, but it's the second half of that data link layer of the OSI model. Logical link control that puts that type field in there. And what this type field is, it's for multiple upper layer protocol support, like IPX. It could also support IPX, IP. It's just an indicator that tells the receiving device what layer 3 protocol was used to package the information up until this point right here. So very important. And this arose later on down the road as devices started to need the need, or they got the need to be able to have multiple upper layer protocol support. Like Novell started supporting IP instead of just IPX. So very important. And again, LAPF down here, and then there's two types of that type field, Cisco and IETF. So when we type in on our interface, when we're getting ready to set up frame relay, we type in the command encapsulation frame relay. I'm just going to cut it short. We could either do a carriage return, and our Cisco router will simply use the Cisco type field. If we have a multi-vendor environment, instead of just hitting carriage return, we would specify IETF as that type field. The IETF type field there is specified in two RFCs, requests for comments. Original RFC 1490 followed by RFC 2427 and specified in the protocol Q933. So you must know these numbers here. 1490, 2427 are the requests for comments that specify the standards for this IETF multi-vendor type field. Let me clean up this slide, and we're going to go in and take a closer look at LMI, Local Management Instrumentation. It is very important not to confuse Layer 2 encapsulation with the LMI type. LMI type performs a keep alive function, letting us know that everything is cool between our DTE and the DCE. And if we had multiple connections on the other end, let's say multiple virtual circuits, it also lets us know the status of our virtual circuits. If we're checking out our virtual circuits on our router, we will see active, inactive, or deleted state. So those are the three statuses we'll see. And our LMIs let us know the status of these virtual circuits. So it's a very important function. There are three different types of local management instrumentation. Cisco, proprietary Cisco. So if we've got Cisco stuff going on, we're good. ITU, also known as Q933A. The A is the big difference here, because I also said the IETF is specified in a protocol Q933, but that is Annex E, a different part of the Q933 protocol, and the LMI type Q933 is Annex A, and that's what the A stands for there. So there is a difference, but they're both supported underneath the Q933 protocol. Again, protocol, set of rules, and then ANSI. So Cisco, ITU, and ANSI. So it's important that we have matching LMI types on our ends here, so we have appropriate communication. Otherwise, our device will think the link is down, things like that. We'll have problems communicating. So very important. LMI is a status message and keep alive function. LAPF is a layer 2 encapsulation. There is a Cisco LMI type and there is a Cisco layer 2 encapsulation. Do not confuse them. Even though the name is Cisco for both, they're two totally separate things, so it's very important not to confuse them. Let's go in and take a look at these DLCIs a little bit further and how they get those numbers. So I brought up a slide here for the global DLCIs, and what's going to happen is our service provider is going to come up with a global map of our DLCIs, and basically the DLCI will represent the destination. So 10 represents the destination. We'll call this Palestra 1 router. 20 represents the destination of Palestra 2 router. 30 represents the destination of Palestra 3 router. Now there are two, let's say we had connectivity between all of the devices here. There's full connectivity going on. So we're paying some money for this full mesh connectivity. Now I color coded everything to make it easy. Blue represents this router. Red represents P3, green represents P2. So what's going to happen is the virtual circuit from P1 going out to P2 is going to have a number on P1 of virtual circuit 20. Now we'll follow this along. And what happens, that DLCI field in the encapsulation for frame relay actually gets swapped in transit. So what's going to happen, this virtual circuit ends up being this virtual circuit right here, blue. But the number's not 20 anymore. The number is 10. How that works is our service provider actually swaps the DLCI out in transit. So when we're sending to 20, our service provider knows it's going all the way over here and going to P2. And what he does is he gets that 20 out of the header and removes it. And before he passes it on to P2, he says, hey, this is from router 10. So the DLCI is one field, and it's actually the source and destination. It just gets swapped in transit by our service provider. So this guy, when he receives information on the same virtual circuit, he'll be seeing a source DLCI of 10, and this guy will see a DLCI of 20. Just like when he wants to send to P3, he'll go out DLCI 30. Cruises all the way along there, and it goes out here, and what he's going to see as the source DLCI is a DLCI of 10. So he'll have a DLCI of 10 and a DLCI of 20. DLCI 10 goes to router P1, Palestra 1. DLCI 20 goes to router Palestra 2. P2 will have a DLCI of 30. 30 goes to Palestra 3, and 10 goes to Palestra 1. So again, to make that clear, or confuse you more, Palestra 2, when he sends out of DLCI 30 or with the destination DLCI 30, remember it's all one physical line. The DLCI is what tells our service provider which virtual circuit it's going to be heading on when it goes to that WAN cloud. So DLCI 30 says, oh, that's got to go over here to Palestra 3. He'll take that DLCI number, the 30 out, and put in 10 as the source, and that way it'll come in on this virtual circuit to Palestra 3. And it'll know where it came from. So it's a global map, and our service provider will help us lay that out. Let's go back and recap all these terms and everything we went over. We talked about the virtual circuits, and again, that is that logical path between our destinations. So we have one router, router A, router B, router C, and he has one line, but he has a connection to B and a connection to C simultaneously. Those connections are called virtual circuits. DTE, my stuff. DCE, service provider stuff. We've got the access link, which is right here. Also local loop, you can call it. Access rate, our speed that they promise us. DLCI, Data Link Connection Identifier, and again, that's the number that represents the virtual circuit. Service provider will tell us what that number is going to be. NBMA, non-broadcast multi-access. Multi-access meaning this one device right here can have access to multiple different destinations through one link. Non-broadcast is he can't send just one message to get to both devices. He'd actually have to send one unicast over each virtual circuit to get to the destination, and that's not a broadcast message. LMI, Local Management Interface, 3 types, Cisco, ANSI, and Q933A. Very important. Remember, do not confuse this LMI type with LAPF. LMI type is a keep alive, also known as notifies us of the status of our virtual circuits. LAPF is a layer 2 meaning OSI model, encapsulation. Do not confuse the two of those. The last thing I want to talk about is IP addressing, and it depends on the links we have. Couple different situations. Because we have these virtual circuits, what we can do is we can create a sub-interface for each virtual circuit. So we'd have our serial interface. This is serial 0, and what we would do is we'd chop it up into sub-interfaces. We could call it serial 0.1 would be one sub-interface, 0.2 another, 0.3 another. And we'll get into this in further detail when we get into configuration of frame relay. But we do want to be aware of the IP addressing concerns depending on how we have this configured. If we have a full mesh environment, meaning everybody can connect to everybody, it's not necessary to create the sub interfaces. We can just configure serial 0 with frame relay encapsulation, give it one IP, 172.16 I want to use, .2.1, 172.16.2.2, 172.16.2.3. We can have one subnet here and everybody share an IP in that one subnet, if we have a full mesh environment happening. Let me clear this off and we'll take a look at what will happen if we don't have a full mesh. Without the full mesh, if we just had a central router, and this is very common, we might have Palestra 1 being the central router, Palestra 2 and Palestra 3 only communicating directly with Palestra 1. In that situation, we would create sub-interfaces out of serial 0. So we'd give serial 0.1, serial 0.2. And this would be considered a point-to-point connection. Each sub-interface would need its own subnet. And our sub-interfaces act like completely separate physical interfaces. And we would assign a DLCI to each interface or virtual circuit. So sub-interface 1, that might have a subnet of 172.16.1.0. Sub-interface 2, 172.16.2.0. So this IP address will be 1.1, 1.2 over here, 1.1, 1.2, but for completely different subnets. So if a system on the far side of Palestra 3 wanted to talk to a system on the far side of Palestra 2, it would have to route through Palestra 1. One other scenario you might run into, let me clean this off one last time here. You might run into an environment, let me draw another switch and router in there. Can you tell which one I drew? So what'll happen is we might have a full mesh environment going on right here. So between Palestra 1, Palestra, we'll call this one Palestra 3, this will be Palestra 2, this is Palestra 4 down here. So we might have communication between Palestra 1, 3, and 4. And then Palestra 2 will only have direct communication with Palestra 1. So in this situation we have an environment where there are 3 routers that have mesh access to each other, 3 to 4, 3 to 1, so on and so forth. And one where it's only a point-to-point, Palestra 2 can only directly connect to Palestra 1. So in that environment, we'd have serial 0, and we'd only chop it up into 2 sub-interfaces as well. Serial 0.1 could go to Palestra 2, and that would be a point-to-point interface. And this would be one subnet. And that could be subnet 172.16.1.0 subnet. The second sub-interface would be multi-point. And what would happen is all 3 of these routers interfaces here would share one subnet themselves. So we do 172.16.2.0. Even though there's multiple virtual circuits going on, they can still share the same IP because they have a simulated broadcast environment. It's non-broadcast. This is the non-broadcast multi-access. This environment isn't really multi-access. It's off by itself, so it needs its own subnet. In this multi-access environment, they can fake the broadcast messages, sending them out multiple virtual circuits, and simulate that broadcast environment so they can all share one IP subnet. So, we have talked about frame relay, much friendlier with it now, what it is, terminology, addressing concerns with frame relay, the point-to-point connections and multi-point connections we just went over, the global DLCI maps, and broadcast handling, what NBMA is, and how that differs from our broadcast multi-access environment with a switch.